Hi, welcome everyone. Thanks for joining us. So it is about 2 o'clock when the webinar should begin. However, we're just going to give it a couple minutes, 3 or 4, just so those late attendees can jump on, log in. So we'll start in around 4 or 5 minutes from 2. Happy Friday, by the way. I don't know if that's a thing, but hope everyone's having a fantastic day thus far. Okay, just a heads up whilst we wait for other people to join. I know some people may not actually be familiar with Zoom. So there is a little panel that should be on your screen. There is a chat box, so you can reference that if you'd like to communicate any information. Over and above that, during the webinar, we'll have a little polling session. So the last session we did, people responded to the poll in the chat. When I run a poll, you'll actually get a dialog box where you can mark your check boxes or your answers to the question. So just be wary of that when it comes up. Righty, so I think that was enough time to get people loaded and logged on into this webinar. So I will begin. Um, Good afternoon, ladies and gentlemen, and welcome to everyone attending our second webinar of the Unstoppable series. My name is Yashin Norin. I am a modular applications engineer forming part of the technical team. Today, we'll be looking at generative design with Inventor and Fusion 360. The main topics for today's session will be an overview of generative design, what it is, why use it, and the benefits of using generative design technology. We will also have a look at how generative design works inside of Fusion 360. Towards the end of the session, we will briefly look at how a generative design workflow can be explored and incorporated with Inventor. A future of more, better with less negative impact on the world brings exciting new opportunities for us in design and manufacturing, but that also means challenges we need to overcome. What are some of the common challenges faced by manufacturers today? With the continuation of an ever-growing population, there comes an inevitable demand for more cars, more smartphones, more highways, and products. It's no wonder manufacturers are struggling to find time to innovate and create new ideas. There is an increasing demand for engineering expertise. This often comes at a costly price. A gap exists between design and manufacturing, limiting the quantity and quality of products we can get out onto the market. Sorry about that. I just heard someone's mic was on for a second. If I could ask everyone just to turn their mics off, please. We will have a period at the end of the session where we can answer some questions and chat a little bit. Okay. So downstream processes are simply not being considered during design, making it increasingly difficult to streamline our manufacturing process. And achieving the right balance between performance and cost is not an easy task. How do we quantify this information to ensure we make the best calculated decisions when it comes down to cost versus performance and developing a new product? Generative design infused into Autodesk applications is the answer to all of these challenges. So what is generative design? Generative design is a design exploration technology combined with artificial intelligence and cloud computing resources, allowing its users to simultaneously generate multiple CAD-ready solutions based on real-world manufacturing constraints and product performance requirements. How does Autodesk's generative design help the product development process? Before we have a look at this, let's review the traditional design approach. Often companies begin the design exploration process by creating a series of concept designs first. These concepts are limited in numbers. We may have 1 to 5 of them. The concepts then undergo evaluation and validation to verify whether they meet performance and manufacturing objectives. The product is then manufactured, produced, and sent out onto the market. However, because of the limited amount of concepts during the initial iteration phase, we find a scenario where the product being produced is identical to the ones being sold by our competitors, eliminating our competitive edge. Another scenario would be from the few concepts explored, none of them meet our manufacturing objectives, either because they're too costly to produce with the chosen method of manufacturing, or we simply do not have the machine technology to make a complex design. This means the iteration phase will have to be revisited, where new ideas will have to be conceived, tested, optimized, and designed until they are believed ready for manufacturing. If they are not ready, the design iteration phase is repeated, increasing the time for a product to reach the market. With generative design, the product cycle is enhanced during the beginning stages of product development. Using AI and cloud computing technology, generative design gives us a choice of hundreds, even thousands of viable solutions that meet our manufacturing performance objectives. Problems are solved for at the beginning. This means we can streamline our product development and significantly reduce the time for a product to reach the market. Time is no longer wasted moving back and forth between concept and design. We can reference the many solutions and make better informed decisions in terms of trade-offs. What would be the best material to use for better performance? What would be the ideal manufacturing method? 2-axis, 3-axis, 5-axis machining, or additive manufacturing? Generative design gives you a broad spectrum of possibilities to ensure we can efficiently produce unique, cost-effective products that exceed our performance expectations. How does generative design work? Take a look at this illustration. It's a great example of the generative design process. Rather than the typical approach to modeling a form, engineers will enter the problem to solve for first. Where's the model being held down? What areas need to be avoided for collisions? What are the loads that it has to withstand? Are there any alternative materials and manufacturing methods that can be explored? Once a problem has been defined, the solutions are solved for in the cloud. This frees up computer resources so engineers can work on other portions of a project. Generative design empowers engineers to explore many more alternatives, then utilize them and build the confidence that they've explored the best design possible. Here is an example of a generative success story. An automotive manufacturer by the name of General Motors was able to successfully redesign a seat bracket using generative design technology in conjunction with additive manufacturing. Generative design was able to deliver 150 design solutions, giving General Motors a variety of potential materials and manufacturing methods to explore. From the design options, General Motors was able to make informed decisions in terms of trade-offs between cost, performance, materials, and methods of manufacturing. In the end, they managed to consolidate the entire seat bracket assembly into just one single part, making it 40% lighter and 20% stronger, exceeding their performance expectations and reducing their labor costs. Using generative design has a host of benefits. As mentioned with the General Motors example, product performance is improved by making components lighter and stronger, increasing their durability and overall lifespan, allowing us to meet and even exceed the needs of our customers by simply providing them better quality products. The second benefit would be an increase in product innovation. Generative technology provides many more design alternatives at the front end of product development. These designs are unique and extend beyond our limited human imagination. Such innovation gives us the edge over competitors and opens doors to new and more business opportunities. The last benefit is the reduction of product costs by simply making more into less, using less parts and raw materials. Now, we are going to have a look at how generative design works inside of Fusion 360. For those that may not know what Fusion 360 is, it is a cloud-based CAM and CAD tool for collaborative product development, used for mechanical design, CAM and FEA simulations, and of course, generative design. The demonstration that will follow shortly after the slide will go through an overview of the generative design process inside of Fusion, touching up on the setup requirements and the definition of objectives that will lead to multiple CAD-ready outcomes. Before we head over to the demonstration, I'm just going to run a quick poll and ask you a question. Okay, so that question is, are your machining operations performed in-house? Are they outsourced, or do you not do any machining? Okay, so I see many people are doing the machining and manufacturing in-house, which is fantastic. Um, the other outliers outsourced, we have one and someone else with no machining. Thank you for that feedback. Okay, so this is the demonstration that we just spoke about. Okay, inside of my Fusion 360 design workspace, you can see I have a pre-designed component on display. Just to give you some background on what this is, it's a triple clamp that fastens the steering shafts or forks of a motorcycle together. Those shafts typically go through these three holes over here. Now, I'm going to take you through an overview of how generative design will allow us to optimize this component and create multiple iterations that will meet our performance and manufacturing criteria we specify inside of Fusion. The first thing we will need is our preserved geometry. This will be the essential or critical portions of the triple clamp that will interact or most likely interact with other components. Next is the obstacle geometry that we'd like to avoid in terms of collisions. Those will be the three shafts going through the clamps. Now we have defined the solids and parameters that generative design will use to build the part. Before we do any solving of the actual design, we need to start defining our problem at the front end of the design process. That problem would be the real-world application of the clamp and all the forces subjected upon it. And of course, we can do this inside of Fusion. I will apply one force on the inner face of one of the ends of the clamp, and that will be a total of 8,000 newtons. We can further define some more performance objectives. Do we want to minimize the mass and lightweight this part? Do you want to maximize its stiffness? We can also choose a minimum safety factor of how much more loading this part will have to withstand. A new change made to generative design in Fusion is the option to define manufacturing objectives. We now have the choice of exploring many more manufacturing methods, or we can limit generative design to create models based on the types of machines we have available. In this dialog box, we can make those definitions. We can choose additive, two-axis cutting, die casting, or alternatively, we can do our milling configurations, whether it be 2.5, 3, or 5-axis machine. And over and above that, we can define the setups that will be used. Once all our objectives and criteria have been made, the data can be generated and solved for in the cloud. We can then explore and filter between all the potential design options, such as the different manufacturing methods, materials, and objective ranges. Comparisons can be made in terms of trade-offs we spoke of earlier by measuring each component against each other. Once the best solution is chosen, a CAD-ready model can be created and used for simulation of CAM operations. And as you can see, we have a couple CAD-ready models already generated. And to
further expand this workflow, what you can then do is use all your manufacturing simulation options, and you'll have a CAM ready model available that can then be manufactured.
Okay, so now that we have a better understanding of generative design and how it works inside of Fusion 360, we can take a closer look at how Inventor users will be able to leverage the benefits and capabilities of generative technology presented by Fusion. This workflow simply allows for Inventor files to be shared with Fusion 360 through a bidirectional link, either by importing or exporting data between the two applications or using the Fusion 360 desktop connector. The desktop connector allows Inventor and Fusion to access the same cloud storage location. This creates an associative link between files. A change made in Inventor will populate through to Fusion and vice versa. Inventor users can now send files to Fusion and explore the many design alternatives that generative design has to offer. Once a suitable design has been found in Fusion, it can be brought back into Inventor and incorporated into the final assembly. So let's head over to the two applications and have a look at this workflow.
Welcome to this demonstration, and what we're going to have a look at is how to incorporate a generative design workflow into Inventor through the use of Fusion 360. Now, as you can see, I do have the two applications open. I have Inventor on one side and Fusion on the other. Now I'm just going to head back over to Inventor, and this is where the workflow starts. We have our designed assembly, and as you can see, it is a front loader. Now, upon closer inspection, you can see there is a component missing in between these links over here. So at the bottom, the pivot point, and at the top where the cylinder is. So what we'd like to do is actually get generative design to create this component for us and optimize it. Maybe lightweight the component, change the type of material for something that's better to manufacture, or maybe use a different manufacturing method that will give us or enhance the performance of this part within this entire system. Now, the next step over here is we've got our assembly. We would like to isolate the key components in order to create the part. So the sub-assembly and maybe any other additional components we may need. And what I've done is created a level of detail of such components. So I'm going to open that up quickly. Once the level of detail is loaded, you can see we have those isolated components on screen. And now we can use this to build the necessary geometry we require to work with generative design. What is that necessary geometry? It's going to be the obstacle geometry as to avoid collisions, as well as the key features, so the preserved geometry that generative design will use to build the part. From the step, once it's been isolated, we simply have to translate this information into a new part file. This is done by using derived. Once we derived it, it's taken into the new part file, and we can start making any additional changes or features that we may require to perform the generative design process. So in this components, I have already created obstacle geometry at this top link over here. Okay, those solid bodies will highlight blue, and over here at the bottom. So all we're missing now is the preserved geometry that the arm will fit around at the center of this pivot point. Now at this stage, we want to get this information into Fusion 360 so we can start the generative design process. There's a couple ways of doing it. You can simply use import and export of the file. So export the file from one application to the other, so from Inventor to Fusion. Or alternatively, we can use Fusion Teams. So what Fusion Teams is going to allow us to do is store this information onto the cloud that both Inventor and Fusion have access to. So there's live data transferring going on here. So what I'm going to do is save this part onto the cloud using my Fusion desktop connector. So the desktop So it works very similar to OneDrive or any of those other file sharing applications. Also very similar to the BIM 360 desktop connector. However, I want to access my Fusion 360 workspace or hub. So I've got a Modena team hub created, and this will open up. All I have to do is locate my project file. So this is a good example where I may be collaborating internally with other members of my team, or collaborating externally with other people. So someone may do the design in Inventor, for example, and then we have another user from a different company that's exploring the generative design workflow. And all I have to do is simply save my part inside the Fusion 360 desktop connector. Once that has been saved, I can head over to Fusion 360 and the file should appear shortly. I may have to run a refresh. Once the data has been transferred, you'll see the file actually load inside of my Fusion. It's called GD1, and it has the little Inventor sigil for IPT file. So it's kind of a shared document, and we can indicate or see those links through that little sigil. And I can just open this up quickly. So that file will then load inside of my Fusion workspace, and what I can start doing now is working on the generative design process. So I'll head over to my generative design workspace. Okay, and it's now loaded, and what we can do is start exploring our generative design study. So defining our performance and manufacturing objectives, as well as defining the parameters of what generative design needs to build this arm that will fit onto the front loader. So this geometry is already there, it's come from Inventor, and we can start defining the essential features. So what is going to be our preserved geometry? We can make those changes, those selections very quickly. So I'm just going to remove the preserved geometry that we'll use later on and highlight all the obstacle geometry that we'd like to avoid in terms of collisions, and those will then highlight red. We can then make the choices for our preserved geometry. Now, what's key over here is you can actually see there is a piece of preserved geometry missing. Okay, so what's going to fit around this pivot axis over here? That hasn't been designed. So like I said previously, we can transfer data from Inventor to Fusion via the Fusion desktop connector, and it bridges a live link. So what happens in Inventor will then populate through to Fusion 360. So remember, this is a bi-directional workflow. It's not one way. Changes made in any of the applications will reflect in the file. So it doesn't just work from Inventor to Fusion or Fusion to Inventor. It's bi-directional. So that part still needs to be created, and what I'm going to do is head over to Fusion and make those design changes and quickly create the pivot axis for the arm over here. Okay, so what's going to fit around this axis? It's going to be a solid body, and I can design that relatively quickly by running an extrude. Okay, so that component's going to extend from this face, and it's going to go all the way up until that point over there. And let's just rotate this a little bit. Okay, so I've made a design change, so I've added some preserved geometry. And what's nice about following this workflow is because we have existing references to work with that come from Inventor, we actually don't have to redesign any of this information. Okay, we can use the reference parameters to build our preserved or additional obstacle geometry if we like. Okay, so that's been created. Let's head over to Fusion 360 to see if that information has pulled through. So you can see it hasn't directly pulled through yet. All I have to do is simply run a refresh, and that part will then be prompted to be updated. Okay, so once that sync has been completed, you'll notice a little sigil appear telling us we need to update the file because changes have been made inside of Inventor. Now, in order to do that, I have to head over to my design workspace quickly and just hit the little update button. So this will take some time to process, and as you'll see, we now have that preserved geometry that will define the pivot point of the arm we're going to create. And we can head over back to our Generative Design workspace. And simply include that as obstacle geometry. So from this point forth, the process is very similar to what we have seen previously in that demonstration of the triple clamp. Now we have simply first off started off defining the obstacle geometry as well as preserved geometry that Generative Design will use to build the part. So we defined the parameters for the AI software to actually build this arm. Next up would be going through the process of defining the real world application of this arm. So all the forces that would be subjected upon it, and we've seen how those have been applied previously. And then depending on all your other performance or manufacturing objectives that you'd like to explore, you can define those here. Okay, once again, just to go over them quickly, we can minimize mass, maximize the stiffness. We can also explore all the different types of manufacturing methods that we'd like to explore, all the ones that we have available that we can use. So usually something like additive manufacturing would give us a higher performing part, but at a greater cost. It also reduces the amount of materials used to create this. So if we want to be a little bit more sustainable, we can do that. We may only have 5-axis machine available for us to use, but we'd still like to get the best performing component out of it. So those are some of the manufacturing constraints. And above that, we can choose between different types of materials. So which one is going to give us or yield better performance? Which one is going to be cheaper to manufacture? Now, I've already set up the study. I'm not going to go through the entire process again. Oops, and we can close that down, unexpected. So I'll head over to a completed example. Once we've gone through the generative design process, we've made all our updates. We have defined all our manufacturing and performance objectives, as well as the problem we would like to solve in terms of the loading conditions. We can then send this to the cloud to generate and explore all the potential or viable solutions that we may receive in accordance to the criteria we have specified. So if you have a look, these are all the outcomes. We have quite a few of them. Generative design can give you up to hundreds, even thousands of potential solutions that we may use for this arm design. So let me just close down that little panel over there so we can have a better look at this. So we can go through the process of making choices. Okay, so like those informed decisions that we spoke of earlier, we can make trade-offs in terms of cost, performance, the best manufacturing method to use, the cheapest manufacturing method to use, the manufacturing method that may yield the better performing components at the best price. So we do have those options here. As I explained previously, you can isolate all the iterations for 2-axis cutting, and those will display on screen, and we can choose between those. We can choose 2.5-axis, 3-axis, 5-axis, die casting, etc. We can also choose between the different types of materials, which one's going to be the cheapest option. And the model that has been designed in generative design will be linked to that material. Lastly, we can just do some more trade-offs. So what is the best mass range that we're looking for? Do we want a mass between 100 and 178 kilograms? And all those solutions that satisfy what I've defined in the filter dialog box will appear on screen. So we do have cost. So what is going to be the cost to manufacture one piece or one item of this arm over here, and that's going to be around about $5, between $4 and $38, and those will be our options. Okay, so once we have explored the results, made our trade-offs, which will be the best component we'd like to use, we can isolate that component, have a look at it, do some comparisons between other components if we like. So generative design will give you those options to make comparisons between all the outcomes and potential solutions for this item that we are producing. And you can see it does have all the definitions, okay, for the part. What does it weigh? What manufacturing method was used to create it? We have a 2-axis cutting option over here versus one that is made out of 3-axis milling. Okay, so we do have a couple choices that generative design will give us to explore. Once we have chosen the design that we'd like to use for the front loader, we can actually generate this as a CAD model. So I do have a couple of these outcomes, and once again, these are CAD ready and CAM ready solutions. So from this point, we could actually take it into simulation to do all the tool parting for the manufacturing that will take place in creating this arm. So we have 1, 2, and 3 outcomes. So this one over here is created using additive manufacturing. As you can see, it's very organic and fluid in shape. The next one we have is 2.5-axis, a little bit more rigid, but probably more cheaper to manufacture. And then we have another one that probably will ideally suit all our manufacturing methods and costs with the correct material. Now, at this stage, what we want to do is get this information to Inventor so we can actually include it into our front-loader design. How would you do that? Save it onto your Fusion 360 desktop connector, and then we can access that information from Inventor. So we're going to head over back to Inventor and have a look at the main assembly once again. So with our main or master assembly open inside of Inventor, we can actually place that component from our Fusion 360 desktop connector very quickly. So I'm just going to head over here. Choose the place component option and head over to my Fusion 360 cloud location where we stored this information. Open up my Modeler Team Hub, access the project folder where the CAD model or the generative design outcome was stored. So what I can do from here is bring that component into Inventor, place and constrain it. It will take a couple seconds to load, of course, because it has to download some information from the cloud and bring it back into Inventor. So what it's doing over here is just converting it to the latest version, okay, and a readable format that can be used inside of Inventor. Okay, and as you can see, I can then go place that component, and of course I could go then and constrain it in place. Okay, so I've already got a couple of these to explore, so you don't really have to worry about that last one that I've created. And what Inventor, or what this will allow us to do through the help of generative design, is explore many design iterations that are suitable for this front loader and all the forces that will be subjected onto the arm that we've created. So you can see it's sort of in position not constrained correctly. So I do have a couple that have already been placed onto this front loader. So I'm just going to turn the visibility of that one off that I've just inserted. And now we can explore all those different design options, okay, while still maintaining the performance objectives of the actual arm. So I'll turn the visibility of this one on, and you can see we have the generative design version. We then have the 5-axis machining option. So generative design will give us more than one option, hundreds, thousands that meet our manufacturing and performance criteria. It has a host of benefits as explained earlier. Now, if you have a look, we've decided on this design and we'd like to make some changes to it. So with this workflow, like I said previously, it's bi-directional. So any change made in Inventor will reflect inside of Fusion 360. So what we're going to have a look at is maybe we actually want to lightweight this component a little bit more. We find that we may have reduced the amount of loads that it's going to be subjected, or the loads that are going to be subjected on it. So I can head over to my Fusion workspace and actually make those design changes very quickly. And what I'm going to do is just cut a hole through this component directly from Fusion 360 and all the way through this arm. Okay, so we have our cut that's been created inside of Fusion. I'm just going to quickly save this part to update any changes that have been made to it. So we've got that cut through the middle of the arm. Now, if I head over back into Inventor, we should see that after we run an update, that this part will then also reflect that change. Check for updates. So you can see changes have been made. There are updates available as, of course, we've made a change inside of Fusion. And this will then reflect inside of Inventor. Okay, so what it's going to do is process that information through the cloud. How does that bridge gap through the Fusion 360 desktop connector, where we can transfer live information between Inventor and Fusion 360. It gives you a host to a whole bunch of collaborative options. So if you have a look, there's our design change. Okay, what we've made in Fusion 360 to further lightweight this arm has been processed and updated into Inventor. I hope you guys enjoyed that workflow. That kind of concludes this demonstration. Thank you very much.
Okay, so that almost concludes the end of this webinar. For now, what we're going to do is open up the floor for any questions. So we're going to have a short Q&A session. There should be a panel in your Zoom settings where you can type any questions that you may have. So feel free to pop those through. I'd also like to introduce one of my colleagues, Helen. She would like to say a few words.
Hi everyone, thanks again for taking your Friday afternoon to join us. I'm the Key Account Manager for Modern OneSolve, and I'd just like to share with you that we have a really amazing promotional offer at the moment, where you get an annual license of Fusion with a 3-day online training course and a license of Twinmotion. And Twinmotion is a rendering application, and you get all of that for 9,995. So just short of 10,000 Rand, you get a year's worth of 2 applications plus training. Thanks, Yashin.
Thanks, Helen, for that. So really does sound like a fantastic deal. Of course, if anyone's interested, feel free to contact us or contact Helen directly. She'll definitely give you some more information on that. So questions, I see no questions have come through yet, so I'll give it a minute or two. But as you can see, Inventor and Fusion are 2 remarkable applications to work with. And often the case is I find we have people using Inventor, and these Inventor users usually have access to the entire product design and manufacturing collection. And in that collection, you have both Inventor and Fusion. So you can start using and exploring these workflows, such as the one that we just showcased, leveraging Fusion's 360 generative design capabilities, and actually combining that with your inventor and all the parts that you may model. Okay, so on that note, I see we don't have any questions. And I'd like to once off just thank everyone for attending, and I hope everyone has a great, fantastic weekend and enjoys their Friday. Cheers, everyone. Bye.